Hi, my name is Brett Threlko, and I'm the Application Manager at Advanced Illumination. I wanted to welcome you to my series, Mastering Machine Vision Inspection, and to take a few minutes to talk about one of the four cornerstones of machine vision illumination. The four cornerstone concept was devised as a teaching tool for labeling and demonstrating four methods that can be applied to enhance or create appropriate image contrast of parts versus their backgrounds. The four cornerstones consist of geometry, pattern and structure, filtering, and wavelength. With proper planning at the beginning stages of your application, geometry is one of the most important of the four cornerstones and the one discipline that you may have the ability to affect the most. However, if proper lighting techniques are an afterthought in your application, it may become the cornerstone which you have the least amount of control over. With proper planning, the goal is to have effective, consistent, and robust features best suited for a given inspection. A frequently asked question concerning the four cornerstones concept is priority of investigation. For example, is wavelength more important than geometry? Should we first be starting with structure, and when do we apply filtering? There's not an easy answer to that question. The steps you take will depend on the part and the expected application-specific results. The geometry and structure are more important when dealing with specular surfaces, whereas the wavelength and filtering are more crucial for color and transparency applications. Understanding how manipulating and enhancing the image contrast from a part against its immediate background using the four cornerstones is crucial for assessing the quality and robustness of the lighting system. Of course, it's not uncommon to find that more than one cornerstone is required to solve an application. System geometry is defined as a spatial relationship between the camera, the light head, and the part or feature of interest. In general, there are two broadly defined system geometries. The first is coaxial lighting. Coaxial implies that the light is centered around the camera's optical axis and as such is commonly referred to as on-axis lighting. This type of lighting consists of dome and tunnel, flat dome, coaxial, and ring lights. We can also consider backlighting as a coaxial variant. Dome lighting is similar to the light on an overcast day. The light comes from multiple directions and multiple angles and helps to minimize the glare. Bear in mind that for dome lights to be effective, they must be very close to the part. Flat domes are considered to be a hybrid of traditional dome and coaxial lights. They are essentially a diffuse sheet of light directed downward and produce more off-axis light rays than a coaxial light, but fewer than a dome light. The flat diffuse light is direct lighting rather than internally reflected from within a dome light to the object. By oversizing the light, you are able to have longer working distances and larger fields of view than dome lighting. In this example, we have a dome light at 50 millimeter working distance. You can see how close we have to be to the part that is being inspected. The image has no glare off of the specular parts and there are no shadows. Here, we have a flat dome light at 220 millimeter working distance. Again, the glare and shadows are minimized. The biggest difference is that the operator is able to manually manipulate the object due to the height of this light. Here you can compare two images and see that they are very similar. While the height of the light working distance has changed, the camera working distance remained the same. Again, to emphasize the point that the greater the working distance with a flat dome, the more that you have to oversize the light to achieve the same result. In a coaxial light, the light is directed at a beam splitter. The light is then directed down at the target and back up to the camera. The light is good for curved or highly topographical objects. The surface texture is emphasized and the angled elevation changes are darkened due to the angled reflections. The ring light is one of the most common front lights used in machine vision. Here is an example of a differing geometry setup of a bright field ring light versus a dark field ring light. Notice the difference in construction and geometry of the two lights. Not only is the bright field ring light farther from the target, creating a more solid light angle, but the LEDs are pointed straight down, whereas the dark field ring is close to the surface and the light pattern is much more aimed. That's due to the LEDs in the dark field ring light being physically aimed at a targeting image during the production of the light. Ring lights offer several key advantages in machine vision applications, making them a popular choice for a variety of tasks. Ring lights can offer uniform illumination, they can help reduce shadows, and increase depth perception. They're versatile, flexible, and easy to set up, and can be mounted directly to the lens or camera. Backlights are good for edge or hole detection. They are useful on translucent materials and can be used for gauging liquid fill levels and inspecting glass or plastic materials for defects. The longer wavelengths may penetrate some objects better. Backlights can be used to check for part presence or absence, location, orientation. For high accuracy gauging, it's best to use shorter wavelength monochromatic light and collimation. Our backlights can be built with collimation film for sharper imaging of edges. Collimation film narrows the emitting angle from approximately 135 degrees on a standard light to approximately 50 degrees on a collimated version. The second broadly defined system geometry is off-axis front lighting. Off-axis lighting can be broken down into two subcategories of lighting, partial bright field and dark field. This type of lighting generally consists of ring lights, spotlights, and bar lights. Bar lights, or linear ray lighting, provide uniform illumination. They consist of multiple LEDs arranged in a straight line, providing a consistent and even spread of light across the target area. This is crucial for tasks like surface inspection where variations in illumination can mask defects or create false positives. They also minimize shadows and hotspots if you have the flexibility to reposition the light. They help you to control the light angle and intensity. For example, you can angle the light to emphasize surface texture. They can be scaled to many different sizes, making them adaptable to different inspection areas. This flexibility allows for a customized lighting setup that caters to your specific needs. This is an example of how switching from on-axis to off-axis with the same light changes the image result. In this first shot, we're using an on-axis lighting and looking straight down using a ring light. As you can see, the reflection of the ring light causes some numbers at the barcode to be obscured. By moving the ring light off-axis and perpendicular to the can, we can change the nature of the reflection, but still do not have an optimum image of the barcode. By moving the ring light off-axis and down the length of the can, we're able to obtain a clear image of the barcode. This method works well with all types of directional lighting. While ring lights excel in broad, shadowless illumination, spotlights offer a different set of advantages in machine vision applications. They can offer us target illumination, be high-intensity light, provide us with increased contrast, allow for adjustable positions, good for emphasizing surface texture. They are compact and easy to integrate and can be cost-effective. The type of inspection using off-axis lighting is generally limited to presence and absence or general location, rather than any measurement for sizes, shapes, or spatial relationships. This is due to the off-axis perspective of the light with respect to the surface and the uneven illumination. In this instance, with the bar light shining from the top down, the surface blemish cannot be seen. However, moving the bar light to a very low angle from the right allows this dent to be detected and for the sheetrock to be rejected. Here's an example of how changing the geometry of lighting can affect the application. In this example, an on-axis ring light was used to try and read the barcode under a piece of cellophane. As you can see, the specular surface reflects the light and makes reading the code impossible. But if we use an off-axis bar light, we can improve the image for the camera in order to read the barcode. Creating contrast changes via geometry involves moving the target, the light, and/or the camera until a suitable configuration is found. This combination of moves is easiest using partial bright field and directional lighting, but can still be accomplished with coaxial lighting. Full bright field tends to require fixed and coaxial alignment positions between the light and the camera. The only thing left at that point is changing the position of the target. How task-specific and ambient light interacts with a part surface is related to many factors, including the surface shape, the geometry, the amount of reflectivity, as well as its composition, topography, and color. Some combination of these factors will determine how much light and in what manner is reflected to the camera, and subsequently available for image acquisition, processing, and measurement or analysis. An important principle to remember is that effective effective application of dark field lighting relies on the fact that much of the low angle light incident on a mirrored surface, less than 45 degrees, that would otherwise flood the scene as a hot spot of glare, is reflected away from rather than toward the camera. We call this principle angle of reflection equals angle of incidence. Using a bright field ring light to illuminate a curved specular surface such as the bottom of a soda can gives us an image with poor contrast and uneven lighting. However, using a diffused light creates an even background and allows the code to be read. Compared side by side, the robust contrast difference is evident. Here is an example of a matte, uneven surface using a 2D dot peen matrix code illuminated by a bright field ring light. When imaged with a low-angle linear dark field light, the light pattern created makes for a more effective and robust inspection. Either of these images as presented would provide a suitable solution. However, any type of stain or discoloration on a bright field image could cause the software to misread the code, but would likely not be seen in the dark field image. Also note that any light technique is generally effective in the geometry-independent portion of the diagram, if it generates the necessary feature-appropriate image contrast consistently. My father started AI in his garage over 30 years ago, and we were the first machine vision LED lighting company in existence. As such, we pride ourselves on being a full customer support company. If you need assistance with an ongoing or a future application, please don't hesitate to reach out to me. I would also encourage you to download our practical guide to machine vision lighting. This comprehensive handbook covers everything I talked about today and much more. If you're looking to get into machine vision lighting industry or would like to refresh principles that you learned in the past, this industry-leading lighting guide is the best place to start. Thank you for your time.